Instrumentation Cables, written and presented by me, Jean Leguay. Here's the legal stuff. This is what we'll be covering in this. I'm not going to read it out because that's really boring. So there's three types of, or three categories of cable that we're going to be dealing with. The first one is comms or communication. Second one is analog signals. They're 0 to 10 volts, 4 to 20 milliamps, that sort of thing. And the third category is digital. These are on-offs, either on-off signals going out to start and stop things like motors and pumps, or on-offs from switches. One of the problem we have with our cabling is that we get interference from other cables. If we run our signal cable alongside, say, a mains cable, then we'll get interference. Magnetic inductive coupling, it's called. That's where the magnetic field in the mains cable interferes with the signals, or actually induces a false signal into our signal cables. The closer the signal is to the interfering cable, the worse the interference will be. Another form of magnetic coupling is electromagnetic RF coupling, RF radio frequency. This is when a radio frequency induces interference in our signal cables. The worst things for doing this are mobile phones and badly installed VSDs. They can induce so much error signal into our cables that we get completely false readings. To cure this problem, we take our cables and we wrap them in a piece of foil. Then we typically run a bare cord down the outside. Then what we do is we earth it at one end. Now it's inside what's called a Faraday's cage, and any interference trying to get in gets caught by the foil and shunted down to earth. Another type of interference is called capacitive coupling. This is because the fact that the cores inside our cables are copper, they're conductors, and they're separated by insulators. Now, conductors separated by insulators, that's a capacitor. So, a field will build between the two conductors. If the red core here goes highly positive, the yellow core will go highly negative by capacitive coupling. It's very distance dependent, so the middle yellow core will be affected much more than the outer yellow core. It doesn't matter if we put foil or insulators between, because the foil just acts like another conductor, and insulators, well, the field goes straight through that. To cure this, we twist the cable. Now, neither one of the cores is nearer than the other, so anything that's induced in one cable will be cancelled out, in one of the loops, will be cancelled out in the next loop. We always screen at one end. The rule we have is that we screen at source. This means that we screen at the source of the power. Typically, this is in the marshalling cabinet, the Mechanical Services Switchboard, the MSSB. So we screen at the switchboard. We only screen at one end. The reason for this is, let's supposing we screen at both ends. Now, let's supposing at this point earth is at 0 volts. And at this point, earth is at 2 volts. Now that's not unusual. It's fairly normal to get earth differences of anything up to 14 volts. So in this case we've only got 2 volts across them. If we was to suppose that the screen had a resistance of 1 ohm, now typically it has a lot less, but I'm just using round numbers, then we'd get a 2 amp current in that screen. It's only a small core. It probably is only capable of taking 2 amps, so we've probably saturated the screen at this point. Now, if a big nasty radio wave comes along, the screen doesn't stop it. It's already saturated. So the big nasty radio wave cuts straight through and ends up inside our signal wires. So for that reason, we only screen at one end. Another type of interference is what we call common impedance coupling. In this example, both of these yellow cores are using the center core as a return. Now if that center core is only capable, let's say we have 1 amp going up one of the yellow cores and 1 amp going up the other yellow core, if the center core is only capable of passing, say, 1.5 amps, then we don't pass the full 2 amps if both of them are on. Let me explain that a bit better. You're sitting at the lights behind a car and he's got a brake light and an indicator light, and his brake's on, and then he turns his indicator on, and as the indicator flashes, the brake light flashes. The reason for that is because they're both using the same common earth, and that earth is not up to carrying enough current. So as the indicator flashes, current goes down there, and now there's not sufficient current going through the brake light, so both lights flash. Another type of interference is common impedance coupling. This is where there is a difference in the earth potential at either end of the cable. It doesn't normally matter unless this is a signal. If I'm sending 4 volts from the near end, and the near end, the earth is a proper earth and it's at 0 volts, and I send it to the far end, and at the far end the earth isn't at 0 volts, it's at say 2 volts, then the signal, which is a 4 volt signal, only looks like 2 volts because it's 2 volts from its local 0, and its local earth is actually at 2 volts. So a 4 volt signal looks like a 2 volt signal. What this translates to is you send out a signal to open a valve 100% and it opens 50%. Unless it rains, in which case all the earths go to the same value, and then it opens 100%. So you have a randomly opening valve. When you make cable, when you make cores, what you do is you get a bit of carbon, a bit of copper rod, and you pull it through a hole, and it makes it thinner. It's a conical hole. And then you pull it through another conical hole and it makes it thinner, and you keep pulling it. So the more times you pull it through more and more holes, the thinner it gets. That's what the American wire gauge is based on. It's basically how many times did we pull it through holes. So the American wire gauge is a number that goes up, and as it goes up, the cable gets thinner. So that 20 gauge cable is 0.8 millimeters diameter, and 24 gauge cable is 0.5 millimeters diameter. Horrible system, but the Americans like it. Now the number of cores. Having more cores in a cable makes it much, much more expensive. However, it does make it more flexible. A solid core, if you bend it backwards and forwards a couple of times, it's very likely to snap, as it gets hardened, it gets annealed by the bending, and it will become brittle and it will snap. In addition to that, electrons like to travel on the surface of the core. So a solid core will carry a lot less current than many multi-cores, because multi-cores have got a lot more surfaces. So the more cores, the more current, basically, with the same amount of copper. Different categories of signal are differently sensitive to interference. Highly sensitive cables are things like comms, RS485, Profibus. Temperature sensors, like thermocouples and thermistors, are sensitive. Things that are less sensitive are the DIs and the DOs. Typically with the DI and DO, we're switching a whacking great big 24 volts on or off. A couple of volts of induction on there doesn't make any difference at all. Stuff which is pretty insensitive are things like AC power and DC power. They're typically quite high voltages, not really going to care much unless you really put a huge induced voltage on them. So, to reduce interference, we twist the pairs and we screen foil and a bare core. We also try and keep things separated. If you have sensitive cables, you try and keep them, say, 75 millimeters, 100 millimeters on plastic conduit, away from highly sensitive cables. If you have this table speaks for itself, really. You just go for it. So we try and keep things a little bit separate. Basically, try not to run signal cable next to mains cable. In fact, don't run signal cable next to mains cable. Try to run them on different tray, different conduit. And always be aware of the rules of segregation as laid out in AS3000. How to terminate cables. Okay, you've got your shields and you've got a core coming off of that. What you should do is you should cut all the shields back, cover the whole end in a nice bit of heat shrink, and then terminate each core with a bootlace ferrule. Unused cores should be before you finish off the bare core, which is going to be the screen, what you do is you loop it round a couple of times. You also tuck any unused cores into that so that they're earthed. The reason you do this is so that they don't become bare conductors, they don't become antennae, picking up interference and adding to capacitive coupling. So the screen wires wrapped round and unused cores are earthed. Nice bit of heat shrink on the outside, a heat shrink on your bare core, which is going to go to your screen. Green heat shrink or yellow heat shrink on that to mark it as a screen. Sometimes we have to have what's called 360 degree screening. If the spec insists on 360 degree screening, and typically it always insists on 360 degree screening if we're connecting anything to a VSD. If this is the case, it needs to be properly screened 360 degrees all the way around the cable. The best way of doing this is either using a surrounding saddle, or the best way, the very best way, is by using a gland, a metal gland piece. Sometimes when we're dealing with cable, they're multi-core, and you need to know the difference between a blue-white and a white-blue. To tell the difference, what you do is you look down the end of the cable. You cut them off and you look down the end. If it's a blue-white, then blue is the main substrate, the underlying colour, and the white is tacked on top. If it's a white-blue, white is the main substrate and blue is tacked on. Comms, communications. There's 3 types of comms. Simplex, this is a broadcast comm. One person is broadcasting to everybody else. One-way communication. The next type is half duplex. This is sort of comms you get with two-way radios. Both people can talk, but only one at a time. And finally, full duplex. This is like a telephone. Both people can talk simultaneously. Two-way continuous communication. Typical types of digital signals that we send out are things like HART, FSK, frequency shifted key, Fieldbus, Profibus, LAN, Ethernet, CBus, BACnet. These are digital communications. Typically, they're using RS485 voltages and the protocol changes. We'll talk about that a little bit later. This is the simplest type of communication, RS232. It's teletype communication, the very earliest type. In its simplest form, you simply have a receive and a transmit and a ground, and the receive and transmit are crossed over. That's with what we call no flow control. With flow control, you have a couple of different extra wires. I don't remember the last time I saw anything using flow control. So typically RS232, you need 3 cores. Anything will do. It's very, very limited distance though. You'll be lucky to run it more than 3 meters. So this is RS232. Now, when we're talking about comms, we talk about the number of bits per second, the speed at which communication occurs. We call that the baud rate. Typical baud rates are quite slow, 56,000. Even on the older units, 9,600. But that doesn't matter, because when we're doing comms, when we're talking to a BMS system or we're talking to a PLC, it doesn't need a lot of information passing backwards and forwards. Now it says here maximum distance 15 meters. That's what it says in the book. Oh, you'll be really lucky to get 15 meters. If you drop the baud rate, you can improve the comms. So if you need to get 15 meters and you can't, if you drop the baud rate right down, you'll find you actually can. An improvement to RS485, 232, sorry, is RS485. With RS485, it has 2 pins for send and 2 pins for receive. So rather than just having the 1 pin for send and 1 pin for receive, with RS485, 1 pin has to go positive at the same time as the other pin goes negative in order to recognize a bit. Typically, RS485 will run 12 mega baud or 32,000 baud, and typically it'll run about 1.2 kilometers or just less than half a mile. It's pretty solid comms, very, very reliable, very, very well bomb-proof. Now I'd like to talk to you about screening. We have to screen our comms. There's 2 schools of thought with screening of comms. The first one is overall screening, where we screen at 1 point and 1 point only, and we maintain continuity of the screening all the way to the end. The second school of thought is what's called the segmental screening, where each individual segment is screened at 1 point and 1 point only. Now, the advantage of overall screening is, well, it's a lot easier. You only need to find one good earth. Whereas with segmental screening, you've got to find a good earth at each point, and that's not always easy. However, if there is a breakdown, let's say, bang, there's a break in the cable there between number 2 and number 3. With overall screening, the comms between 3, 4 and 5 completely breaks down. I mean, obviously 3, 4 and 5 can't talk to 1 and 2, but they can't talk to each other either. Whereas with segmental screening, 1 and 2 can talk to each other, and 3, 4 and 5 can all talk to each other. So, although the network is broken into 2, it's broken into 2 functional networks. Sometimes when we need to extend the signal, we can either use a repeater or a router. What a repeater does is, well, it repeats. It takes a very low power signal in, and it just boosts that signal up and sends it out. The problem with a repeater is it just boosts everything. So if it's getting interference or rubbish signals, it just boosts them up and sends a boosted interference signal down the line. The alternative to a repeater is what's called a router. What a router does is it gets signals in, and it will only send signals that make sense to the other side. And it will only send signals if the receiver is actually on the other side. So, analog signals. These are 4 to 20 milliamps, or more commonly in HVAC 0 to 10 volts. They're from things like thermocouples, thermistors, sensors, that sort of thing. And they go out to things like actuators. Now, for this, we need individually screened twisted pairs, 0.2 to 0.4 millimeter squared. Digital signals, these are coming from switches and going out to contactors and relays. Overall screened, so one screen around all of them. Overall screened twisted pairs, 0.4 to 1 millimeter. If you're going to be doing anything high powered or high voltage, then we're going to be using interposing relays in between. We don't bring high power and high voltage into our controllers. Earthing. Earthing is probably the main cause of faults. Okay, so never ever use the power supply off the controller, off of the BMS controller or off of the PLC. That is a bad idea. Always have a good external power supply, a good clean power supply. And always make sure everything goes to the earth. So if you have a DC power supply, which is supplying the instruments, you then have another DC power supply for the solenoids. The reason for this is, as the solenoids bang in and out, you don't want the interference which they will cause to go down the line and upset the instruments. If you have AC solenoids, you have another earth for those. And of course the AC earth is connected to the main chassis, to the box. If you're in an intrinsic safety area, I should have said, the DC earths are all connected to the master instrument ground bar, and that has its own connection to the plant ground bar. The AC earth goes to its own master safety ground bar, and that has its own connection to the plant ground bar. If you're in an intrinsic safety area, you have some intrinsically safe instruments, that has its own earth, and that is independently connected to the plant ground bar. Earth connections are by nice big fat cables, at least 6 millimeter cross section. The biggest cause of faults I've ever seen, the most common cause of faults is earthing. In fact, most instrument problems, it's usually quoted at 95%, are down to poor insulation, poor power supply and poor grounding. It leads to interference and noise. And that's the end. Thanks for listening.